Hi everyone. Welcome to 3.2. We're going to be talking about balanced binary search trees. Now, this is probably a very welcome topic for some people because, we've just spent like 2.5 hours talking about binary search trees, and um, a big part of what a big part of what we were doing was talking about how they're not balanced sometimes. So we know how to insert into. Sorry, I was running up and down the stairs in the break, and I'm very unfit, so I'm like a little bit puffy. But we know how to insert into them. We know how to delete them. We know how to traverse them. But we also know that if we do things the wrong way, kind of circa this first slide deck, where we talked about insertions, if we insert them the wrong way, we might end up with a tree like this, or a tree heading towards this. And we don't want that, right? We want our trees to remain balanced. So this is pretty much what I've just said. Binary search trees will often slowly lead to a more imbalanced tree, to more imbalanced trees, so we need to develop strategies to prevent that. All of these strategies are based off of a notion called tree rotations, which is what we're going to spend a while talking about, and then there are two particular ways that we can apply tree rotations. This is this is just a little bit more context on why this matters. And the reason is because, again, like this is exactly what we said before, but let's talk about it in terms of time complexity. A balanced tree has log n search cost, which is great because the height's log n. But in the worst case, if the keys are inserted in ascending or descending order directly, we end up with on and essentially a linked list, right? In reality, you rarely will ever have a totally balanced tree because the cost involved is so great. Like, having an imbalanced tree with a couple of extra levels is not going to totally ruin your search cost, right? It's still going to be log n-ish. But also, we don't want it to head towards on. And there's a very fine line here because every single time we rebalance a tree, it costs us something. It takes time to do. Every single time that you don't rebalance it, though, it takes like more time to kind of look up. So this kind of essentially does come back to this notion of amortization that we talked about, which is essentially trying to do more work in advance so that we have to do less work later. And this all fits into that topic. Now, formally, the definition of a balanced binary search tree is that for all nodes, this here means for all nodes, the absolute value of the number of nodes in the left subtree minus the number of nodes in the right subtree is less than 2. That's what a balanced tree is, and this is for all nodes. Now though, I've kind of worried myself that the title of this is wrong because that might be a weight balance. So there's two types of balances that we're going to talk about a bit, and I think I clarify this later on, but there's this notion of weight balanced trees and there's this notion of height balanced trees. And height balanced trees have the same height on both sides, but they have different weights on both sides. So like a height balanced tree, if I can delete all of these, like a height balanced tree could be something like this, where you have like lots of nodes in one side, and then on the other side you have this. And they're all like, all branches, all leaves here have the same height, but their weight is wrong. So height's pretty much like, are both of my subtrees the same height from the root for all nodes? And a weight balance tree is there the same number of nodes on both sides? So a weight balance tree, right? This, 1, 2, 3, 4, 5, 6, this is now a weight balance tree. So this is no longer a height balance tree in this case, right? This is a weight balance tree. Whereas before it was like a height balance tree. So this definition here, I'm pretty sure, is actually weight balance tree. I haven't really clarified that here because there are two types of balancing we can deal with. And there are advantages to like having both of these kinds of things. Like a weight balance tree will kind of help you add in a more balanced fashion as you go. A height balance tree will help make the search cost a lot more consistent because it's the height that determines the worst case search cost. And yeah, autumnal says, why is this less than 2? And the reason is pretty simple. It's because when you're building a tree, it's inevitable that there's at least one level of difference. Because like, okay, this is a balanced tree, but this is also a balanced tree. And so is this, and like so is this, and so forth. And the reason for that is just because like at some point the tree is going to be imbalanced if you define it as like they all have to have the exact same height. Whereas like here, what you have is you kind of have like, you know, this one ends at 2, this one ends at 2, this one ends at 2, and this one ends at 1, right? Like a null here. So in this case, it's still balanced because, you know, that's just the nature of trees. It can't be perfect all the time. But the point is that the second you do this, it's now unbalanced. Because there's a height difference between here and down here. Because you should have found a way to theoretically insert this new node like here or something. Because, you know, you do a whole level at a time, and then you expand out the next level, and then only once the whole next level is full do you keep going down. Now, there are 4 things that we're going to be talking about when it comes to balanced trees. There's one which is what we call left rotation, and another one called right rotation. These are very simple operations that allow us to essentially take a tree and restructure it in constant time if we know where the actual node is. Similar to all the deletions as well. Most of the cost in balancing a binary search tree comes from actually finding the nodes you want to rebalance, or doing many of these rebalancing. But the actual effort of modifying a binary search tree is actually quite quick. So we're going to talk about left and right rotation. Now, left and right rotation are then both used to do more complicated types of rebalancing, which is an insertion at root rebalance method and a partitioning method. So we'll first get on to our rotations. So the way that a tree rotation works is a tree rotation is essentially taking a particular node in a tree and swapping it around a little bit. These operations, I believe, well, I'll answer that question later. So let's just first get a more like practical understanding of what rotating a tree means. Like when we say we're going to rotate a tree, remember that with binary search trees, a tree is literally just a node with children. And in fact, all nodes here are trees, right? 5's a tree with 4, you know, children and grandchildren. 6 is a tree with no children. 3's a tree with 2 children. 2 and 4 are a tree with no children. They're all trees. So when we say tree rotation, we're really saying that for a particular node, we're going to rotate it. Now, there's a ton of different ways that people can think about tree rotations. And I've got one I've written up here. There's another way of thinking about it. And to be perfectly honest with you, like having taught this course a few times, my advice for you is to go and look at examples that we provide in like these slides and stuff, and just keep look at it, follow it, take a break, like don't look at it anymore, write the nodes down, try and rotate it yourself correctly, look back, see if you got it right, and eventually you'll build your own kind of process and habits in your head about how to do this. Effectively, and this is not how I think about it, effectively what happens with a right rotation is that when you take a number 5 and you try and rotate it right, what you're really saying is you're trying to push 5 down to the right and bring other things up, which in fact actually kind of creates a rotation. And it's kind of funny because if I copy all of this here, and then I grab something, oops, that's kind of ugly. I grab something like this here, and then I try and rotate it, say 90 degrees. That's kind of what we're doing, right? Like, see that? How we're actually like just taking that 5 and we're kind of just twisting the whole thing. So when we say we're rotating 5 twice, the way I like to personally think about it is that 5, whenever we say we're rotating 5 is like at the pivot of a circle, and we're essentially taking what's to its left and we're trying to rotate it around to the right. So it's like I'm taking 5, like I'm putting my hand on 5 and I'm literally twisting the tree a little bit. And what that's doing is that's pulling 3 up the top here. Now, that part itself is kind of a little bit intuitive. You're like, okay, you rotate 5 right, you kind of take what's on its left and you twist it up, right? You rotate it right by bringing it up over. You take what's on the left and you rotate it around. The hard part is some of the tree reorganization that happens. And this is really honestly the difficult part of tree rotations. And what's really great is that your tutor will have other ways of explaining this to you and probably better ways of explaining this to you. So there's lots of different kind of things you'll understand. Now, these red arrows here essentially show you the link changes that occur during rotation. So what happens is when you rotate 5 to the right, you're essentially moving 5 down and having 3 point to it as its child. And then the 4 is now a child of 5. So again, I never think about it like this. Like I would never sit down and like replace these lines and like change the arrows. But functionally, this is the change that happens before we redraw the tree. Right? So what effectively happens is that when you, and I'll just again, we'll look at this in Paint here. When you rotate a node 5, there are really only a couple of things that undergo any kind of change. And that is the 5, its left child, and its left child's right child. These 3 things are kind of what changes during a rotation. Everything else stays the same. And you can kind of see this, right? Like, we'll look at 2 here. 2 at the end of the rotation is still a child of 3. As far as 2 is concerned, nothing's changed. 6 is still a child of 5, so nothing's changed. The only things we're really modifying are just these 3. And that's true no matter how big the tree is, right? So even if this had like hundreds of children, you still only do a rotation on these 3 elements. So for a rotate right, it's the left child and its right child. And all we do is we bring 5 down. So like kind of how I think about it is like, we're gonna, I wish there was a polygonal tool, but I'll make do with this. We go and we bring 5 down like this. I might get rid of all of this for a second. We take our 5 and our 6. We bring that down like this. We take our 3. It comes up to the root. And then we rearrange who 4 points to. And I might make these thicker as well so you can actually see them. So they're the steps that happen. Right, you rearrange it like that. Now again, some of you are going to be like, oh, that makes sense, and some of you aren't. And like, personally, I'm one of those people that, finds these things kind of hard to understand. Waleed says, Waleed, is making statements, not questions. And yeah, you can approach it a lot intuitively. Like, okay, well, let's say you rethink it another way and you say, okay, well, all I personally remember with rotations is that when I rotate 5 and I twist the 3 up around it, that clearly what must happen here is that like my 5 and 6 comes down below the 3. This is all my brain does like that. But then you can ask yourself, how does this tree going to look now? Like, you don't even need to remember the operations, which is what Waleed's kind of get at. It's like a binary search tree. Everything to the left has to be smaller. So it's like, where is 4 going to get pointed to now? It can't be from the 3, because 3 is like smaller than 4. So 4 has to be in the right subtree now. It just like has to be. So therefore, it's going to be a child of 5. So like even if all you remember is that initial bit where you just like take the 5, rotate the 3 above it, which is essentially swapping the pointer, you can actually figure out the rest intuitively. And that's another way you can think about it, which some of you might prefer, is like, if you're rotating the 5 right, which is taking the 3 and rotating it up, you might just swap around that arrow, which is what's happening here. You swap around that arrow and you say, oh, 3's the root now, and then you kind of redraw the tree and you'll see that something doesn't really make sense. So again, my advice is look at a bunch of examples, look at the tutes, look at the lecture notes, and you'll eventually, like, you do it 5 or 6 times. And even me, like, I haven't really looked at tree rebalancing, because that's not really something I do day to day, for like 2 years, right? And this probably took me, I think I looked at it two weeks ago, and then I looked at it a few days after that, and then I looked at it again a few days after that, and I was like, okay, I think it's like finally ingrained into my head. So don't put too much pressure on yourself here. ZG says, can we promote the largest number from the left-hand side subtree to the root in this case? I'm not sure. Are you talking about the left-hand side subtree to the root? I'm not too sure, sorry, what you're referring to. But I think another thing to note is that in all these lecture slides we have, again, we're often dealing with these really small trees. But in reality, when we're moving 4 here, we're actually moving 4 and its entire subtree, right? So in an example like this, if 4, for instance, has like a whole tree under it, like this, when we move it across, that whole tree is now over here. So we're actually moving, like, not the 4 node, but the entire tree. This is true for pretty much all BST operations, so nothing particularly new here at all. But that's the essence of a tree rotation. When you say rotate 5, you take the 5, you literally rotate it to the right, which brings its left child up, and then you just rearrange some pointers. And there's not many you need to rearrange. And the reason we say, and we'll get to this at the end of this little deck of slides, but we'll see at the end that this is constant time operation because you're only ever modifying these 3 nodes. Like, no matter how big the subtree is, once you know what you're rotating, it's a constant time operation. So let's look at some more examples. When we do a left rotation, we do the exact opposite thing. So what a left rotation is it's taking a node like 3, which we're rotating left here, right? So this is literally how I think of it in my head. As I like put my fingers on 3 and I try and picture rotating it left, and I think about what happens in that case. You know, in this case, like 5 gets dragged up, and other people will think of it differently. When they say rotate left, they might think 3 gets rotated left underneath the 5, right? Tons of different things. So in this case, we rotate 3 left, which is going to bring 5 up to its root. So like even without me looking at the next 2 bits, I'm just looking at number 1 here. If I think about this intuitively, again, I'll look at this and I'll say, okay, well, if I'm going to be rotating 3 left, then what's going to happen is I'm going to be bringing it down here, and I'm going to be bringing like 5 and stuff up to the root. But now I know that like for 4 has to be in the other tree, so 4 comes back down here. And there's the rotation, like it's done now. That was it. And you see we only had to modify those 2 lines, which are the relationship between 3 and 5 and 3 and 4. So that's kind of what a left and a right rotation is. And again, if it's a lot to take in, then don't think about it too much yet. You can keep looking at it, don't stress. When I said didn't think about it too much, I just meant don't stress too much. This is what a tree looks like when you rotate it right, then you rotate it left again. I think the important thing to note here is that if you take 5 in a tree and rotate it right, and you take that 5 and you rotate it left, it doesn't end up where it started. Because what's actually happening here is we're rotating 5 to the right, and then we're rotating 3 to the left to get this back here. Okay, so yeah, in this case, like, just be aware that, you know, you rotate right, you rotate left. Formally, you would describe the process like this, right? You would say that the process is that if this is your tree down the bottom here, that N1 is your current root, N2 is the root of the left subtree, N1 gets a new left sub. Like, you could kind of step through it like this. And personally, I don't find these explanations that useful until you have an intuitive understanding of it. Like, when I look at this now, as opposed to even just 3 weeks ago when I was like trying to refresh my brain from a couple of years, I look at this diagram and I think, what's happening here, right? Like, what's all this T1 and stuff? And now I look at it and I'm like, oh, this makes perfect sense to me. And this description here also makes perfect sense. This is more just showing you the actual step-by-step operation that you would then say go and derive pseudocode from. So pseudocode might come out of this, for instance. This is another tree rotation example. What I like about this tree rotation example is that you actually see some more subtrees. It's a little bit more complicated. So like if we again look at this one here together, and in fact, let me just get rid of that right subtree because we'll just, we'll try and create that. When they say we want to rotate N1 to the right, okay, we want to rotate 24 here to the right. You can think about this different ways. For me again, the way I think about that is that, when I think about that, that's like I want to bring my entire left subtree here, and I want to bring it up, right? Like I want to like rotate it left up here, such that I know that 10 is now pointing to 24. So I've essentially reversed that entire operation. It used to point the other way. And then I say, okay, well, this doesn't make sense, so I'm going to have to like drag this 14 down here because it has to be in the right subtree now, and there's my rotation. So it's just kind of two pointer changes essentially. First one's rotate it up. Second one is like rejoin that straggler, that weird out of place, ugly duckling, black swan, whatever words carry that connotation. And there's your rotation. It's actually really straightforward. Once you know like where to go, it's like quite a straightforward operation that you can repeat many times. If it's making sense in this lecture already, then like great job. I mean, I think that's awesome. And it'll make sense pretty quick too. And once you have to like actually do it on pen and paper. Like I did this in Paint. I'd look at it and be like, all right, we're gonna balance this, and then I'd do what I just did, and I'd be like, is that the tree we got? Yay, I got it right. And then you kind of get it. Do that a few times, and you'll be fine. So tree rotation algorithms. These are the two tree rotation algorithms. They always take in a root, which is essentially just a node, because I think just for clarity here, when it says root, don't mistake that in thinking that you have to give it the root of like an entire tree, right? Like you don't have to give it like, if you have this tree and you want to rotate a random node, it's not saying the root of the whole tree, it's saying that node in particular, because remember, every node is itself a subtree, right? So just keep that in mind, because that's very relevant. So right rotation or left rotation. Well, firstly, if you look at the difference here, they've just swapped all the lefts and the right. So like once you kind of get the gist of rotation in the code sense, you can easily change it around to like two different operations. But you can see that the way rotate right works here, which we'll just do it to keep simple, is that you say that, and let me just reverse this, because we were rotating this one right, weren't we? Yep. So let's say in this case the root is n1. This is the root. The new root, right? So currently the root, I'll do it here. The root points to this, 24. First thing we do, the new root is the root's left child. Okay, that's easy enough. I'm going to make the root point here. Okay, so that's the new root of my tree. Then I check, is the root, this is the root that was passed in, not the new root, is the root empty? Or is the new root empty? Okay, in the case where the root's empty or the new root's empty, you just return this, I think. Yeah, like if either of them are empty, it's like it's not really a rotation, right? These are just the standard checks that you have at the start of a lot of these functions. Then we take the root's left child and we point it to the new root's right child. Root's left child should now point to new root's right child. So root left child should now point to new root's right child. So that makes sense. So 24 should now point here. So they're doing things in a slightly different way to what I've just been like visually doing with you. Okay? Then we say that the new root's right child, so the new root's right child should now point to root. So the new root's right child here should point to root. And then we would have to kind of rearrange how this is displayed visually to make it make sense. Like that. Because yeah, then you'd have to like take this whole thing here and basically just drag this down, and then that would be what the new tree looks like, and that's exactly the same thing. Surely you'd want to, Matthew says, surely you'd want to check if root is empty before making new root. Yes, probably. Some pseudocode omits some things, and that might be the wrong way around. I see what you're saying. Yeah, you could. I mean, you would then just have two separate if statements, I think. If you were coding this, you would probably do that, yep. Because otherwise this would segfault here, right? Like anytime you're dereferencing a potentially null pointer, you face a segfault. So that's a rotation. Now, cost of rotation is cheap. It's 0.1. And the reason it's cheap is because all the rotation requires is a simple localized pointer rearrangement. If you look at the pseudocode, there's no loops. Pretty much any time there's no loops or there's no recursion, it's always 0.1. That's like a very general rule. Because if there's no loops and there's no recursion, it means that the number of operations you do will not scale as the input size or the data structure size scales. So it's all 0.1. However, in reality, when we're actually using rotations, we'll often be applying it many times in a tree. So essentially, as we're about to learn in the next slides, even though the cost of the rotation is 0.1, if you're doing many rotations, that's when the actual time complexity gets bigger than 0.1, because you're doing it maybe on n nodes or some number of nodes. Jed asked a question, which was why make balanced tree to unbalanced tree? Oh yeah, just to demonstrate rotation. Yeah, that was it. It was just like, yeah, we're not worrying about like looking at tree rotations is totally in a vacuum. It's not really like balanced or whatever. It's literally like this is the basic primitive operation that you do. And now we're looking at using it to actually create balanced structures. Ask me that question towards the end, Waleed, and I'll try and give it the brain space for it. Now, there are two key methods of using rotations to balance trees, and this one is possibly one of the most basic ones, and it's this idea of insertion at root. And insertion at root's really interesting because the idea of this is that when you have a tree, right, like, I don't know, where's a tree? Sure, we have a tree here somewhere. There we go, that'll do. I still got it saved. When you have a tree like this, whenever we insert things, you know that if I tell you to insert 11, you'll go bam, 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 and you'll insert 11 here like this. That's where you'll put it. So every time you insert, based on the binary search tree lecture we've done, you're always inserting at the leaf. You're always putting it down the bottom of the tree. Now, one thing we can do to make trees more balanced is to insert it at the root, at the top of the tree. Now, inserting at the top of the tree doesn't mean that we just like insert it up here and we're like, oh, there's 11, great. I'll just like put this here and then change how these are pointed and scribble that out. There's my new root. That's not how insertion at root works. It sounds quick, right? You might not be aware why it solves a problem, but it's like this won't work because you can see that in the left subtree there are numbers bigger than 11. So that's not good. That's not what we want. So what an insertion at root essentially is what we do is we do it in two parts. The first part is we take a node like 11, we insert it where we know we have to, down here, and then we use tree rotations to slowly and gradually bring it up to the root. Because a tree rotation, as you've probably seen from these other examples, is essentially a way to move something up the tree. Like, think about what's happened here. In this tree rotation, we have moved 5 further down the tree and we've moved 3 further up the tree. So if you ever want to move 3 up the tree, you can just rotate its parent to the right. Or if you want to move 6 up the tree, you can rotate its parent to the left. Or if I wanted to move 4 up the tree, I would rotate its parent to the left. And 2 up the tree, I'd rotate its parent to the right. Right? So right rotate brings the left child up, right? Same thing. As Autumnal said here. So that's what we're doing here. So the method is you insert a new node at the leaf of a tree, and then you lift it up the tree through a series of rotations until it's at the root. Now, the benefit of an insertion at tree, and I'm not saying this guarantees being balanced, but it definitely helps, is that recently inserted items are close to the root, and in a lot of data structures, recently inserted items are actually searched more often, just by, I think that often makes sense, because you insert something and then you might be checking it or working with it for a little bit. You can rotate, and Jay's asked, can you only rotate the root or you can rotate any node? You can rotate any node in the tree. So whenever we say like you can rotate a tree, again, so whenever we say tree rotation, every node is also a tree, because a tree is a recursive data structure. So tree rotation, node rotation mean the exact same thing. And again, the point of insertion at root, right? The point of even balancing a tree, no one cares how a tree looks, right? Like, oh, a balanced tree is really pretty. I care about how it looks, but no one should care about how it looks. But a balanced tree is faster to look up. So part of the benefit of insertion at root is that it makes it fast to look up recently inserted items. And it actually can help balance things a bit. Depends on the inputs. There's a lot of factors that play into it. The disadvantages, though, are that every time you insert, you have to rearrange the whole tree. Right? So you don't just insert a number now, you have to insert then do a whole series of rotations. Waleed says, how did you bring up 4? How would you bring up 4? So if I was to bring up 4, and we'll do an example about this in a sec, is I would rotate 3 to the left, which would replace, it would move the 4 up here, and then I would rotate 5 to the right, and that would bring the 4 up here and then here. Okay, so insertion at root. Let's have a look. I painstakingly drew out all this. Is probably the next 5 slides are probably the most effort I put into the slides this term, because I draw these little circles because I wasn't satisfied with any of the examples we had, because I think this is hard to get your head around. Is that let's say we want to insert 24 into a tree. Okay, so we have this tree on the left here where the root's 10, and it's a little bit imbalanced. It has a height difference of 2 because 5's here and 29 and stuff's down here, so it's imbalanced. It's height imbalanced and it's weight imbalanced, both of those things. And we want to insert 24, right? No, I did not use PowerPoint to draw these. It's just a tool that I use, and I'm kind of sucked into it because I can't really show you now, but yeah. Anyway, it's PowerPoint. Yeah, it's basically PowerPoint. It's like making it in PowerPoint. It's be no different. It took like 10 minutes. I'm not trying to paint myself as a saint. Anyway, it's just some circles. So let's say I wanted to insert 24 into the tree. First thing I do is I'd insert it as a leaf, just like a normal insert, right? And that is you follow down. 24 is greater than 10, greater than 14, less than 30, less than 29. There it is, 24. So I put it in. That's stage 1 of insertion at root. The next stage of insertion at root is I start to rotate it back up the tree. Now when you rotate, you can only rotate right and left. And essentially all we're doing is just looking at its parent and figuring out which way to rotate it. Like, we know we want to move 24 up. And to move 24 up, you have to rotate its parent. Okay, so which way do we rotate its parent? Well, again, I think about it as I put my hand on 29 and I think about if all of its children are like attached, which way do I have to rotate 29 to bring it up quickly? You know, so in this case, I think about rotating 29 to the right. Again, other people think about it like rotating 29 to the right brings it down, or like whatever. So rotating 29 to the right, let me move my stupid head. We rotate 29 to the right, which does exactly what we know it does. It means that 24 goes where 29 is, and we have to rearrange it like this. You could step through that algorithm again if you wanted to. For rotations where there's only one child, it's pretty easy, because you can literally just swap them and then make sure that it's the right thing. Like, you don't even need to think too heavily about it. So now we've got 24 one step further up the tree. We want to keep moving it up the tree. So what's the next operation we're going to do? Well, we need to rotate 24's parent. 24's parent here is 30. So we've got to rotate 30, but which direction? Well, I think about it again. I think, okay, I want 24 to swing up. So I think, okay, 30's got to get rotated right. So essentially what these slides are is like the right-hand side moves down to the left-hand side here. So it's like one operation at a time. So now this 24 gets rotated up. So if I just I'm not looking at the right-hand side yet because I don't want to, I'm just going to try and tackle this intuitively. I have something like this, and I want to rotate it right. I want to rotate 30 right. Well, what do I know happens here? I know that this gets dragged down. 24 and 29 kind of come up here. But then 29 is clearly less than 30, so it comes down there. And that's probably my rotation. That makes sense. That follows the rules. You could be more methodical about it. That was a very intuitive rotate. And that's how we get what's on the right here. So we rotate that up. I'll answer a couple of these questions soon. And then what's the next step? Well, we want to rotate 24's parent again. You're always rotating the node's parent. So 14, I'm going to rotate that one left because I want to swing 24 up around like that. So I'm going to rotate that one left. And this is what I end up with. I rotate it left. Single node rotations are easy because, the 14 just comes down there. And then the last thing is I want to get it to the root. So I get 24's new parent, which is 10. And I want to rotate it now also to the left because I want to swing it up around that way. as if it was rotating left up around. And now I get left with this. Now this tree just happens to have magically looked really pretty after this balance. Like, don't get this impression that every insert at root will just magically make all of the trees look really nice like that. Though in this case it has, where again, because this one has two children, I'll just touch on this. We have this, and then we're going to we're going to rotate 10 up, 24 up. So again, similar thing. I take this, I move that down, 24 goes up here, and then I think, well, 14 is going to have to get rearranged, so 14 ends up attached there, and then these are our new pointers. This is the pseudocode. This is where things get, I think, a little bit complicated for my brain at least. Autumnal says, if having recent items be easy to access is important, then wouldn't a linked list with insertions at the head make more sense? I don't think it would make more sense. Like, there are circumstances where that could be also very beneficial. Though if it's not at the head, then your time complexity of search would go way up. Autumnal also says, would you need a parent pointer to do this, like a doubly linked list? So that's a great question, because clearly Autumnal's looking at this and seeing that I'm saying things like we take 24 as parent, and when you think about a one-directional structure, you think, oh god, how do I get the parent? And you could store a parent pointer like you do with doubly linked lists. That'd be possible. Though in reality, what probably ends up happening more is that because this is a recursive algorithm, or even if it was iterative, you kind of, by nature of traversing through it and unwinding the recursive calls, you kind of know where the parent is at all times, and we might see that in the pseudocode. And Jay says, will every rotation move the child node up one level? Yes, it will. So going from bottom to top will be ON. Exactly. And I might jump straight ahead to complexity. You can see here that the complexity of an insertion at root is O of height as well, or OH. That's interesting, right? Because, and this is a cool example of big O notation, is that insertion is OH, right? Because to insert a node, not this method, just a normal insertion, takes OH steps in the worst case, because you have to traverse down the whole tree. Insertion at root is also OH, because you do an insertion down the tree, you do the insertion at the leaf, and then you unwind and you do all the rotations up. And each of those is a step. So effectively, it's kind of 2H, or like 2 times H, because you have to go down and up. But because of big O notation, it is also OH, right? Because we know that 2H is H. Like, you get rid of those coefficients. So this is actually a really great example of where you need to be aware that big O notation is a simplification that helps you understand the nature of how algorithms, how long they take, the change in how long they take as the input grows. So in this case here, it's twice as slow than an insertion. But a billion numbers, like, what's, like, let's say we have a billion number tree, which is log 2 of a billion. It's 30 operations. 30 operations, which is ridiculously quick. Like, a computer could do 10 million of those in a second. So, suddenly now it's going to take, instead of like a 10 millionth of a second, it takes like a 5 millionth of a second, right? So that's kind of why big O notation exists, because like in a lot of situations, you don't really care about the coefficient. Not always, but what's this? For applications where the same element is looked up many times, you can consider moving the node to the root where it's found during the search. Yes, this is really interesting, because this is something else you can do, right? Is like, this isn't just insert and then rotate to the root. They're actual, I haven't seen them personally, but I know there are algorithms out there that if you have a tree structure and you're searching up a particular element, if the data structure is detecting that you're searching up the same element all the time, it might either could cache it, but that's more complicated. It might actually rotate it up to the root so that lookups are really quick. Now, in terms of the pseudocode here, this is a recursive structure. And what I think I want to show you here, and this has only just crossed my brain, to be totally honest, which I didn't think about before, is that I want you to have a look at our, take a look at this interesting thing. Have a look at these two algorithms. Don't they look awfully similar? Well, I mean, it makes sense. They're both insertions, but we already talked about our binary tree insert, where essentially, if the tree is empty, then that's where you insert it, right? And you kind of recursively call this function as you go down. And if the tree is not empty, then you go left or right, and you... Oh, I gotta sneeze. You go left or right, and you call the function on itself. What's happening here is a very similar thing. Now, the pseudocode's a little bit different. That's totally fine, because there's no structure to pseudocode necessarily. It's just like you just trying to explain things. So, sorry, this one is interesting, because it's like... Yeah, anyway, so I really like this, because one question I get a lot is students saying, is this pseudocode right, or like something pseudocode? And I really like that these two things kind of do the same thing, but they're written a little bit differently. Like, they're using capital tree or tree here or something like that. Because that's kind of the point of this, is that it's not, there's no structured thing. We don't expect you to follow a structure. We don't have like these variable names. I've had a tendency this term to start writing a lot of my pseudocode in lecture notes like Python. I'll show you what some of the previous lecture notes had, which are fine. They're a little bit more verbose, which probably makes them a little bit clearer. So like these are some tree join things, right? So this is some other pseudocode, is like, and you'll see like the difference here is that it's nearly, I don't know, VBA style. Like it's like if and while, there's no braces. It's kind of like nearly shell scripting. Yeah, and there's some input and output information as well. So these are both totally fine. Different. Some of them might have advantages or not, but I think it's a good demonstration that, these are just different things. But here's what you notice about this, is that this is an insertion, a recursive insertion function. And recursive insertion essentially does just take a tree, look at its children, and then recursively call the insert until it gets to the bottom. But what's really interesting here, and you're going to have to think back to what we learned about pre-order, post-order stuff, traversal, because this recursive algorithm, I think, is really key to understanding. Like, if you don't understand this, I think a lot of things are difficult. So if you didn't get your head around this with the printing, it's one of the few things I'd actually say, like, make sure you get your head around in the next week or two, because the idea of recursively doing something and the order in which your action is, whether it's before or after, that has a big impact on things. So what's actually happening here is that we insert, say, the left child, and then we keep calling this function again, and when it's finally found the root, it actually unwinds. And as it unwinds, it does these rotations. Because if I take this, let me just undo this tree for a sec. If I take, oh, that code's so tiny. So cute. So if I take this bit of code here and I call it for node 10, right? So I call it for node 10 here, which is the root. That's too big. Let's do a better color. And I call it for node 10. What happens is it goes through the code and it gets to this line. Sorry, it gets to this line here, which is else if item that I'm inserting, which is say 24. Actually, let's pretend that we're inserting a new number. This will be a bit easier. Let's pretend we're inserting 11. So I'm going to try and insert 11. So item is always 11 in every recursive call because you just pass the same item down through all the recursive calls. Say we're inserting at the root, which is 10. Okay, so we're inserting into tree the root, which is the 10 node here, and we're inserting 11 into it. We would get to this else if block here where we check the item is greater than the root's value. That's correct. 11 is greater than the value 10, which is the root or the node's value. So what we would do is we would then call insert at root on the child's right tree. So what happens is this entire function, right, this is how recursive stacks work. This entire function gets called again right on this line here. And it gets called again with 11 as the item. And it gets called with 24 as the new root, right, because it's being called in a subtree. So, 24, great. The tree's not empty. We check, is the item 11 less than the new root's value? It is, because 11 is less than 24. So then what happens is that we call insert at root again on, oops, sorry, my line before was wrong. This line here should be here, my bad. Just ignore that part. So we call it again here on the new subtree. This is how recursion works. It's a little bit messy. I'm sorry for the slightly imperfect structure here. So we call it again. Same item as 11, except the subtree this time is 14. Okay, 14's not null. 14's greater than the item. So we do one last call, and let me just expand this out so we can see more. Come on. We do one last call where we call the recursive call on null, right? Because we check 14 is greater than the root's value, so we make one more recursive call where we've just given it 14's left child, right? Because that's what, wait, tree's right child. Oh, I think I might have been linking these the wrong way. I'm sorry, but that's okay. I mean, you get the point. It's one of the recursive calls. Sorry, I think I just looked at that wrong. So the recursive call gets made again for null, right? Because when you pass the child here, 14, when you pass that child there, it's null. And what does it do if it's null? It inserts the new node. That's what it does. So null here gets replaced with the new node, which is 11, and now it's a shiny new node. And then the function returns tree. So this function returns tree, which passes it back up to this function here. And you can see, what does this function here do when it returns? It rotates right. Okay, because the recursive call returned. Again, I'm sorry that some of these lines don't perfectly match up to function calls. I got them back to front. But the rotate right happens now as it unwinds the recursion. And we haven't needed to keep track of a parent or whatever, because now we're back where 14's the root, and we simply rotate the root to the right. So then, you know, this becomes 11 and this becomes 14. And then it returns the new tree, which is 11. And then it unwinds to 24. Right? And as it's unwinded here, as this function has returned, now it actually does the rotate right on the tree 24, which rotates it up so that, you know, it changes around. And then that returns the new tree, which then returns back to this function of 10. Do you know what I mean? So it's like, the way it works is it's kind of like insert until you hit the base case. And then the base case returns. And then as you're unwinding all these returns, you're executing that next line, which is the rotate. So it's kind of like traverse, do something, and as you unwind, rotate. So this is another example where recursion is really beautiful, because we talk about recursion back in week 1 and we're like, ooh, Fibonacci and stuff, and it's like, great, that was really helpful. But this is where the elegance of recursion really comes into things. Waleed says, is this post-order or pre-order? I don't really want to call it post-order or pre-order because we're not traversing the whole tree per se. Like, I think post-order and pre-order makes sense when you're trying to explore everything. But this is post-order-esque in the sense that we are doing the work on the node after we've explored everything we want to, essentially. And that's how I think about post-order, is like, whenever you're doing a whole tree traversal, you always have work to do. This one is saying, do the work, then explore the left and the right. do the like explore the left, do the work, and explore the right. And then post order is saying do all the work, and then once you come back up, sorry, post order is saying explore all of the tree, and once you're done, then we'll do the work on this node. So that's like, it's post order-esque in that sense. Yeah, so really, 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 really interesting, I think. Last couple of topics, we got 10 minutes. Tree partitioning. This one is like understanding rotations is kind of the hard part of this lecture. So another idea with rebalancing is picking an element in the tree and deciding that that's the new root, and then rebalancing everything around that, which you just basically do through rotation. So I'll give you an example. Let's look at an unbalanced tree somewhere. Where's an unbalanced tree? I feel we might have seen one somewhere. Here we go. That looks like a beautiful unbalanced tree. If we have an unbalanced tree like this, you could index the nodes pre-order style. Pre-order style just means like, you know, from the smallest to the largest. From the left to the right, I think. Is that it? Am I going crazy? No, it's from the smallest to the largest. Yeah, you could rearrange it smallest to largest. You could say this is index. Ooh, that's a big freaking number. You could say, okay, this is index 0, this is index 1, this is index 2, this is index 3, this is index 4, this is index 5, and index 6. Maybe you could search the tree to do this. I'm not sure. I'm not sure where these numbers come from. Let's pretend you search the tree pre-order and you just keep a record of this, or you you know, something. What tree partitioning does is it's a way of saying for a particular index, let's rotate that to the top. And if we partition it about the middle element, then it's going to be balanced, at least weight balanced, right? Maybe not height balanced, but it's definitely going to be like weight balanced. So in this case here, tree partitioning would say, let's take this tree, no insertions, just the tree as it is, and we say, let's find the middle element by index, the middle sized element, the median element, and let's rotate it up to the root. And what that'll guarantee is that because everything less than 24, like in this tree, the middle element, which is 24, there are an equal number of nodes less than 24 and an equal number of nodes greater than 24. Both of those things are true. Well, I mean, both those things are the same, which makes it true. So when we do a tree partition, all we're actually doing, it's really straightforward, is we are finding an element, we're finding an element in the tree, which is typically the median element, and we're rotating it to the root. And that partitions the tree into two sides on either side of that root, and that's why we call it partitioning, right? Because partitioning is to separate two things. So we're separating this chunk of numbers and this chunk of numbers about the index that we're interested in. And this is an example of it, right? If you want to partition the tree around 29, which is closer to the middle than 10, because you see like 29 here is, you know, 3, 4, 5, whereas 10 is just 1, 0. So 29 is a little closer to the middle. The middle two elements here are 14 and 29. So if you actually were to petition about this, you would get, you would get a roughly weight balanced tree. Now at the start here, I said that petitioning gets you a weight balanced tree. That's true if there's an odd number of elements. If there's like an even number of elements, then naturally one of those sides will have to have more. And in general, there is this correlation between weight balance and height balance in the sense that something that's weight balanced is more likely to be height balanced, I would say, generally, and vice versa. So here, in the attempt to make this more weight balanced, we've actually made it height balanced. So this is a height balanced tree now, because the level here is 2, 2, 2, and 1. So essentially it's all, this is still weight balanced, but yes, yeah, I said before that weight balance is when they're totally equal. In reality, it's when they're less than a threshold. I think we talk about weight balance more next lecture. Yeah, so Jay says, can you please describe the rotations to do this? Yeah, sure, I'll do them quickly. So in this case here, if we want to partition about the third index, which is 29, then the rotations that you would do here, that you want to move 29 up, so you would rotate 30 to the right. So 30 would come down here, 29 would move up. There's no left child for 29, so there's nothing to do. Then you would rotate 29's parent 14 left, which would bring 29 up. And it would essentially do this, and you would have to rejoin these oh, I picked white as my color for some reason. You would rejoin these like this, and then you would take 29's parent 10 and you would rotate it left. And when you rotate it left, you would have to bring it down, which would then force you to bring 14 down as well. Now I'm rushing through that mainly just for time, but that's the process. You could take that more slowly and apply the principles more rigorously, but that's kind of the steps you would take. Would you rotate or break and then rejoin? So I don't think you could break and rejoin, because deleting a node and rejoining will only reorganize the tree and everything under it, right? So if you delete like the node 30, nothing above 30 in the tree changes, only things under it. Yeah. This is the code for it. It's pretty simple. I'm not going to go through it. It looks very similar to insert, right? You explore the tree looking for a particular index, and then once you find it, as you unwind, you rotate back. So it's very similar to insert. It's like you go somewhere and then you rotate on the way back to bring it up to the root. And then the time complexity is the same kind of thing. It's all OH. Because, the worst case is that the thing you're trying to partition about, like this one, is at the bottom of the tree. So that's why the worst case is OH as well. Quick question, then we'll do the last slide. Wally says, is this Inorder Traversal? So Wally's referring to... What are you referring to? You're referring to me doing the indexes, right? So that's a good question. So before, what happened was I had a tree and I assigned indexes to everything. And I think the slide said indexes are based on pre-order. So I'm not gonna lie. Yeah, it should be... Oh, I see what you're saying. Yeah, that's true. That's just a typo. Yeah, so the indexes are placed on in order. And the reason for this, again, I really like to emphasize this in order pre-order thing, is that the way that you traverse trees is always the same. You always go down the left and then the next and then the next. It's all about when you do the work. It's all about when you do the work on the tree. So if I just get rid of these for a second, maybe this is a great chance to demonstrate it one more time. Is if I was to label these in a pre-order way, which is to do the work, then do the left, and then do the right. That's what pre-order is. What that means is that when I say the work, in this case, it's literally labeling it. That's all it is. So in this case, I'd say, well, okay, I'm going to start the root. This is 0, so I've done the work. And then I explore the left. And the left here is recursive. I do the work here, so this is 1. So I do the work on this one, and then I do the left, and then I do it here, and then I do the left, and then here. And then I explore the right, left of this tree, there's nothing. I explore the right, there's nothing. So I unwind. I've done the work on C, I've explored the left of C, now I'm going to explore the right, but there's nothing, and I do the same thing. And then when I come up to E, I explore the right here, and that's this is how pre-order gets formed. Because you do the work as soon as you see the node. Inorder traversal is the exact same thing. You follow the exact same traversal, it's just when you do the work on the node. So for instance, inorder here is left, work, right. So I go to this node, I explore left. I get to this node, I explore left. I get to this node, I explore left, because we're trying to do all the left searching before we insert anything. I get to this node, I explore the left, there's nothing there. Then I do the work, 0. Then I explore the right, there's nothing there. So then I come back up. For C, I explore the right. Oh, sorry, before I explore the right, I do the work. There's nothing there. I explore the right. Come back up. We've done the left on E, now we do the work. Then we explore the right. For H, I do the left before the work. For F, I do the left before the work, but there's nothing there. Then I do the work. Then I explore the right. There's nothing there. I come back up. I've done the left, so now I do the work, and then I do the right. Okay, so all of these different things are they're always the same traversal. You're always going left until you can't, then you're going right till you can't, then you're unwinding. It's just, where do you do that slice of work? In this case, the work is indexing something. Last thing, sorry, I know there's probably some more questions, but this is pretty much it. This is really quick, there's this other notion of periodic rebalancing, which we're not really covering in any depth in this course, but it's an interesting concept, which is the idea that you partition, but you do it selectively. So partitioning a tree is a great way to weight balance the tree, which helps with height balancing, where you just say, okay, pick the median index, rebalance the whole thing. It's an OH operation. But you don't want to do it every insert, because that's probably overkill. And you don't really want to do it too infrequently, because then you're not getting the benefit of it. So a common way is that you would just do a rebalance every K inserts. So let's say you have this tree and you just say, all right, every 1,000 inserts, I'm going to, partition my tree about the middle element. And you can do this by keeping track of nodes. You can do this a bunch of ways. You could keep some kind of external counter. This one is actually just doing the rebalance every time there's another 100 nodes in the tree after insert. But yeah, there are a ton of different ways you could do it. But the point is that these are all fundamental concepts. Rotations, inserting at the root, partitioning. You can use them in a whole bunch of ways to a whole bunch of different frequencies. That's totally up to the circumstances and what they demand from you. How do you do height balance? We will talk a bit more about that next week when we look at AVL trees. So let's talk about that more next week. But I hope, just to wrap up, I hope this has been a fun little introduction into trees. I think this is one of the first truly new things that you're learning in this course that's like quite meaty. So if you're feeling like you kind of are following this okay, then I think you're on the right track, which is really good. I will answer Waleed's question, but I want to wrap up the recording first. So this is the Balanced Trees lecture. If you could please take the photo thing, do it with the phone. Can I tell you a secret? I did not realize that you could use your camera to scan QR codes until like literally 4 months ago. I always thought there was like a QR code app that you had to download. Maybe it was like 12 months ago, but like even a year ago is still like, it was probably a year ago actually now, because it was like at the start of COVID. But it's like, I don't know how I managed to avoid that for all these years of my life. I just didn't scan QR codes. I was like, I don't have the app for it. And then one day I just thought about what they were. And my friend just took a photo of one and it was like, and I was like, oh my God. Autumnal says my grandparents had been taking a photo of each COVID QR code, but never scanning it. That's so funny. You did used to need to use an app. That's maybe why. Maybe I was just a dinosaur. But anyway, this is the end of the Balanced Trees lecture, so thank you.